Okay, another proof. This is of 12.3. Basically, with this one, we need to show that a constrained critical point C that's restricted to the manifold M exists if and only if there are M Lagrange multipliers. So this one is, I'm going to flip around the camera here. So basically, we need to show that this relationship holds, that basically we can write our derivative of our little f function, our objective function, as the linear combination of our m rows of our derivative of our big F constraint function. So basically, we first, the direction that we prove Lagrange multipliers imply constrained critical points. So a little notation guide here, which Paul uses. I don't know how helpful it is, but I'm using it for part of this proof anyways. Basically, here is derivative of the big F constraint function, and here are the m rows associated with it. Here is the derivative of the little f function, which, because it's only going from Rm Rn to R, it's only got one row. Okay, so let's just see what we got here. So we have that if V is an element of the tangent space of M, then we have that we've showed previously that this means that it's an element of the kernel of D big F. And then we also have that because it's an element of the kernel, then basically if I multiply this by that, I get for all of the i's alpha sub I times the vector V is equal to 0. So basically, because I can rewrite my beta, my d little f, as just this linear combination, I get that it is equal to 0 and everything is 0. So V, the vector, is an element of the kern of V, which is the kern of d f sub c. So we have a constrained critical point. So that isn't too hard. The other way around, the opposite direction, to show that constrained critical points imply that there must be Lagrange multipliers. Basically, in this case, we're going to do the contrapositive. So we're assuming, just to make things simple, that our D big of F is onto. So that means that the rows of the D big of F are all independent. And then we construct this B matrix, which is basically just we stack the D F big F on top of the D little f. Now, because it has m plus 1 rows that are independent, that also means that it has m plus 1 columns that are independent. So B, which is a function taking us from Rn to m plus 1, is onto. Because it's onto, basically, this vector in m plus 1, we can find some vector V. So B times V is equal to this. But then, of course, we have that, since we have all of these zeros, our alpha 1 times V, etc., that's all equal to 0. But then our beta, the row vector times V, is equal to 1. So that means that V is not in the kern of D little f, but it is in the kern of D big F, which implies that D big F is not a subspace of D little f. And of course, we need it to be a subspace in order for this to be a constrained extremum, a constrained critical point, I should say. So basically, we have that no Lagrange multipliers implies no critical points, and the contrapositive is that critical points imply that you must have Lagrange multipliers. So actually, I think this proof isn't too bad, except for the fact that the notation is actually a little bit confusing. And I think the notation is mostly for the more complex case that's discussed in Hubbard, so I understand why it was included in the class notes. But that is the proof.